anyway, thanks for setting this up, Tuin, and we appreciate your technical expertise on the back end here, setting up the meeting and the YouTube live streaming and the Slack channels for interaction from folks who are viewing. We want to welcome all who are viewing. I noticed that there are at least 50 people registered for this webinar, and that doesn't surprise me because Michael Bloem is a person who has spoken a few times in the past to our group and to other groups, and is always a person who generates a lot of interest and questions. In fact, I think that I've observed more than once that Michael is the presenter who has elicited the most questions in his presentations that I've ever heard, and that is a clear indication of quality and interest. So we're delighted to have him back. I'll briefly say a few things in introduction of you, Michael, if that's okay.
Sure.
So Michael comes from Grand Rapids and has returned to Grand Rapids, shall we say. Michael graduated from Calvin College and then got a master's degree at University of Illinois and followed that with a doctorate from Stanford University. I think in the course of that doctorate, you did some work on aviation operations research in the area of aviation, and then later worked at NASA Ames Research Center.
Yeah, I worked there during my PhD studies. Yep.
But we are fortunate to have Michael back in this region in West Michigan. Michael worked for several years for Steelcase in the area of advanced analytics there, and now is a principal data scientist at Mosaic Data Science. And we look forward to hearing what you have to say now. Michael's a person who's always curious and seems to be always engaged in learning something new and applying new tools and techniques to new problems. So this is exciting. Tuin, is there anything we should also announce to the community before we get started with Michael's presentation?
Sure. So are you able to hear me?
Yes.
Okay. Thank you again, and thank you again to Michael for providing this interesting content. And as you mentioned, pretty much all of his presentations are very, very interesting, and it's much more needed at times like these when people have a limited outlet of going out and conferring with professionals in the area. So we understand that, and we are thankful that we can at least do conferences like these. In light of that, some of you might know that Big Data Ignite, which happens once a year, typically around September. This year as well, we are planning to take it virtual, and we are working on a webinar series. There'll be more information about it on the web, so stay tuned on that. That's all I have.
Sounds good. So with that, let's get right into the meat of things. We'll turn it over to Michael. If you'd like to say anything else about yourself or about Mosaic Data Science by way of introduction, feel free. And then we'll look forward to learning something about machine learning.
Thanks, Elliot. Yeah, excited to be with you virtually again, and excited to talk about improved machine learning workflows with Kedro and MLflow. If you have questions as I go along, feel free to put those in the Slack channel. I think Thomas will be keeping an eye on that, and I'll pause in a few moments during the talk to respond to any questions that moderator Thomas thinks are particularly worthwhile. So with that, let me jump in here, and I'll share with you my main message, something I hope you can remember from my talk today. Machine learning model development workflows and model life cycles can be complex, but tools like Kedro MLflow and scikit-learn pipelines can help manage that complexity, thereby helping ML models to more efficiently deliver value. So hopefully through the course of this talk, you'll start to understand what I mean by all that, and be able to remember that as you work on machine learning models that you're trying to deploy and use to deliver value in some sense. So the way I'll structure the talk today is around opportunities for improvements to machine learning workflows. In the course of my career recently, I've encountered these opportunities for improvement and regarding machine learning workflows, deploying a machine learning model in some sense. And along the way, I had the chance to explore some tools that can help address them. And so the opportunities for improvements are source data ambiguity, non-uniform machine learning pipeline code, for collaborative tracking of model parameters and performance, Clumsy model handoff for deployment, and re-implementation of feature calculations for deployment. For each of these, I will provide a little vignette or example of how they popped up in my career to make them more tangible and hopefully more interesting to you. And then I will also talk about how some of these tools can help address these challenges. The first two can be addressed by using some capabilities offered by Kedro. The next two can be addressed by using some capabilities offered by MLflow, and the final one can be addressed by leveraging some capabilities in scikit-learn, especially the scikit-learn pipelines. So we'll start with the source data ambiguity, and I'll tell you about this by sharing a snippet from a chat interaction I had with a colleague, redacted here, who we were talking about how she had finally kind of achieved the performance that we were expecting from a particular model. And I asked her, how did you fix that? And she tells me, you wouldn't believe it. The data set I was using was from the beginning. It was the old one, the little one we started with that only had 6,000 records instead of the larger 60,000 one. And that's why the model wasn't behaving as we expected. So somehow we had, lost track of, who was using which version of the data set. And I don't know if this has ever happened to you, but this sort of thing has happened to me many times in my career. And this was just sort of the most recent time that there was some ambiguity about what source data set was being used when, and it led to some issues with getting a machine learning model moving forward. Kedro offers a capability that can prevent that or reduce the risk of that. It's called the data catalog. And the data catalog kind of abstracts away data loading that could involve various file formats and file systems and maybe look a little different per operating system even. It's declarative, so you kind of declare things very clearly up front, very organized. It has a kind of cool and slick way of keeping track of different versions of data sets, if that's important to you. And I'll talk more about pipelines and nodes as we go along, but these entries in the data catalog enter your pipeline for your machine learning model as an input to some of the nodes in that pipeline. So to make this more concrete for you, I have this sample project that hopefully you all have the link to if you want to explore it. It's a simple iris problem. So it's a very famous kind of machine learning problem where you have this data describing like the leaves or petals on a plant, and you're trying to classify what plant it is based on those measurements. And this Kedro software comes with that little demo. So I took that and kind of extended it. And here's the data catalog for it. It's very simple in this case. You just have this example iris data. You specify where it is here. It's an O1 rock, iris.csv. And the type of data set is a pandas CSV data set that just specifies when you refer to it behind the scenes, it's going to be loaded up into a pandas data frame using the pandas tool set. Now, there's all sorts of other things that can be in a data catalog, and a lot of those are mentioned here in the comments. You can have a SQL table data set, a Spark data set. I'm going to flip over and just give you a quick glimpse at a data catalog on a project that I've been working on for my job where we are predicting the taxi times of aircraft. So how long do they spend taxiing, like say after they land and until they get to the gate. And in this case, we have a lot more complexity in our data catalog. There's different data sets that might exist in different versions. One's like when it's from the database, one's when it's CSV that you've already queried. You can specify things like start and end times for your SQL queries. We have just more items declared here, I suppose, different database items or CSV items. So that's what a maybe more realistic example of a data catalog might look like. But all those things are declared kind of in one spot, and it's easier to keep track of what you're working on and when, thanks to the data catalog. All right, so the next example I'll talk about is or opportunity for improvement, non-uniform machine learning pipeline code. And this came up for me in another project at work where we were looking at predicting departure runways for flights. Those aren't assigned until after the flight kind of pushes back, usually from the gate. So we were trying to predict those departure runways ahead of time, and also kind of how long it would take to taxi to that runway before, from the gate out to when you take off. So these are two very closely related models. One actually feeds into the next one, and I was working with these that a couple other data scientists developed, and my role in this case was to extend them to an additional airport. And so I was reading their documentation and their pipelines, and in one case, data scientist number one with the runway prediction model had a nice README, and it had various steps called out here. Activate your Anaconda environment for running this code, and then you're going to run these Python scripts in this order. And they all take a particular file, configuration file. If you look at that configuration file, it has stuff like, okay, what runways are available at this airport. There's specification of like file paths that are appropriate to this particular model. So a reasonable structure here. Data scientist number two, working kind of in parallel on a closely related model, had a kind of very different structure. I mean, not entirely different, but they had their own set of scripts that needed to be run and had different data elements passing between them. A configuration file that had a lot of the same things. There's quite a bit of duplication here, and different assumptions about sort of the file structure and how things would be set up. Both of these worked well, and it wasn't like a huge deal for me to pick them up and start using them, but they were different, and that can be problematic or lead to some inefficiencies because I had to try to understand them, kind of wrap my mind around their approach, and it also, so it's a little bit harder to get up to speed basically when everyone's using these different workflows. There's Kedro offers something that helps address this, which is the uniformity that it kind of enforces around the project structure, inspired by a template for data science projects called the cookie cutter template. And I've included a screenshot of that file structure here. I won't go into detail about this, but it's a nice structure, that has different parts of your source data for manipulating the data, building features, building models, visualizing things, places for your data, and so forth. Kedro extends that. In particular, the project data structure is based on a fairly sophisticated data engineering convention that Quantum Black, the organization that developed Kedro, came up with, and you can see that described here in this table. Again, I won't go into detail on all this, but they've, I think, put quite a bit of thought into how they set up the projects. And just as a note, these data layers, you'll see them when I show you the examples here, existing like on my local computer, but you can also apply these in some cloud-hosted, S3 bucket or something like that. And another note, I'll talk in a minute about how MLflow helps with some of these opportunities for improvement. And with MLflow, we'll store models somewhere else. But let me just show you a little bit about what this looks like, this project structure. So this is just the top level view of the repo here. And you can see, for example, if we go to the data folder here, we have their clearly defined, structure going from raw and beyond. And that's going to look the same in every project. Under source, you'll find there's always a test folder right there for running your tests, and then there's your more kind of project machine learning code here that always has these nodes and pipelines, and I'll talk a little bit more about those in a minute. So that's what it looks like on that Iris project. And if we flip over to the kind of real taxi in prediction project I talked about before, you'll see over here on the left in my IDE the exact same structure where I have my raw data here and some other more processed data here. Again, I have my source, and in here I can find my main ML code, and then the nodes and the pipelines folders. So it takes some time to kind of get used to it, but it's always the same. I mean, I show up in this very different project, and I see the same folder structure, and it's a little bit easier to kind of get up to speed and start working with it quickly. All right. Few more items, other ways that Kedro sort of enforces uniformity. Parameters, both of the examples I talked to you about before had a configuration file or a parameters file. Kedro has the same thing, just always kind of named the same and in the same place. And you can also pass in any of those parameters as a command line argument. These parameters enter pipelines as input to nodes, just like the entries from the data catalog do. So you can just refer to a parameter in kind of an abstracted way when you're building a node or putting nodes together into a pipeline. And just as a note, with MLflow, we'll additionally log all the parameters used in any given run, so we can go back and know what parameters we were using. So if we look at what those parameters look like for our little Iris project here, there's not much, but we have, okay, how do we want to do our train test split? How much data do we want to hold off for testing the models? We have something I'll talk about later. How do we want to deal with our standard scaler that kind of prepares some of our data for modeling? And then we have model parameters. So these are various parameters that are used in our logistic regression model that I haven't shown you, but that's how the model knows kind of how to train itself. Now, if we go over to the taxi-in project, again, we have the same parameters file, and it's, of course, a YAML the format here is very flexible, but you'll see some similarities. Like here, we have one of the models that's involved in this sort of suite of taxi-in time models. And you can see, we have the model parameters, and these are some of the same sorts of model parameters that go into a scikit-learn model, as you saw for the logistic regression model. And there's a bunch of other stuff that is relevant. What airport are we dealing with? The start and end dates, things like that. So that's the parameters file. Another way you get some uniformity out of using Kedro. And then nodes and pipelines. This is maybe the biggest or most important one. So when you're working in Kedro, the way what you end up doing is putting all your data, parameters, and code into a directed acyclic graph that can describe the analyses you're doing. And so what that means is, another thing that means is that you're kind of capturing all your data manipulation, model training, et cetera, as nodes in this graph. And that can encourage reuse. It sort of makes you build little functions that carry out everything. And then there's a single command that runs the entire pipeline or portions of it. And so it's always the same when you want to run a project, whether it's your little Iris project or something else. So I'll just show you a few examples of some nodes and pipelines. So in like the data engineering here, you can see we have a split data node that takes in our data, and then a parameter, the train test ratio, what fraction of the data do we want to set aside for testing, and returns a dictionary. And so this all this is doing is breaking apart the data into training, X data, and training target or Y data, and then testing same. I have another node here for standardizing the features. So you sometimes want to ensure all your features have mean 0 and standard deviation 1. That can help with accelerating training or maybe model interpretability. And that's another node that we have here. And then these are stitched together into a data engineering pipeline. And there's actually 2 data engineering pipelines, one with and one without that standard scaler. I'll show you the one with the scaling, and then you'll just see you're making a pipeline here, and it has 2 nodes. First one uses that split data function. You tell it what the inputs are. One of them is an entry from our data catalog. The other is an entry from our parameters file, and Kedro will know how to go off and get those and load them and use them. And then what it spits out here is mapped to some named outputs, which can become inputs in the downstream. So you'll see this not scaled train X and not scaled test X show up down here. And then they become inputs to the standardized feature node in this little pipeline. These example train Y, test Y, train X, test X then will show up as inputs to the data science pipeline. Go down here, we see those same names that we saw before. This train model node also gets all of our parameters that it uses to train the model, and it outputs something called the example model, which is then used to make predictions, and finally, those predictions are used in reporting accuracy. So all of this is just kind of a way to stitch together functions and do so in kind of a rigorous and pretty clear way. Here's that train model node or function that I just showed you as part of the pipeline. I won't go into what this is doing in detail yet, but the main thing is it does like a model.fit. So it's fitting your model based on that data.
Hey, Michael.
Yeah.
Do you have a minute to take a couple of questions?
Yeah, I'm almost to the end of this section, so why don't we just wait till I get to the end of this section, and then we'll do it. So the last thing, which should be pretty quick here, is I'll show you that here. So there's a nice plugin, Kedro Viz plugin, that makes these pretty kind of pictures of your pipelines that you can click on and zoom around on and so forth. I find these mainly useful for communicating with others about the pipelines. So here's my colleague sending me a chat message with an image, a screenshot of her most recent pipeline, and kind of asking, is this what yours look like? And so we've started using this more to communicate with each other about our pipelines. And here is the pipeline for the Iris project. You have your data coming in here, your parameters. Here's the split data. Here's where you standardize the features, and then you get your training and testing X, and the train Y and train X flow into train model along with the parameters. You get your model. That, along with the test X, is used to make a prediction. So you have your example predictions, which you then compare against the test Y in your report accuracy node. So that's what the pipeline looks like in this little example project. On our other kind of more real world pipeline looks like this. It has a lot more nodes, so a lot more data engineering going on, a fair amount more kind of complexity in getting ready to train the model, more testing going on at the end. So that, of course, can be much larger. All right, so that brings us to the close of the first section here of the talk, and a good chance to take some questions. So what do we have?
Okay, I got one question from Julia, and this is actually a bit back here. She asked, generally, what are you placing in intermediate versus process? And then she goes on to ask, for you, what constitutes that layer of saving?
Are you talking about...
I think that was back when you were on the uniformity and improvement for Kedro parameters, I believe.
Oh, okay.
It was probably 5-10 minutes ago.
Okay. can't say I fully understand the question there. Oh, the folders in the Kedro structure. Okay, so I think that's probably like referring to this structure here. And yeah, I'd encourage you to just follow this link and read up on their data engineering convention. To be honest, I'm still sort of wrapping my mind around it. They do talk about, I guess they don't say much more than this table. So, we can read the table here. Looks like intermediate is optional data models, which are introduced to your raw data models. So maybe converting string-based values into their current typed representation. I've really only used myself raw and primary. So here you've done some like transformation and wrangling to get something that's more ready for feature engineering. And then feature is like once you've actually engineered and calculated the features and it's like almost ready to go into the model. Yeah, I guess I don't fully understand all the distinctions between these layers, but hopefully this table here can provide some guidance on how to use them.
Okay, and then Tony asks, in terms of the concept of uniformity of the ML pipeline, does Kedro offer anything for keeping libraries consistent across developers? For example, 2 data scientists might want to be working on different versions of Panda.
Sure. Well, that's potentially a big problem, and Kedro tries to handle that using requirements. So Kedro prefers to work with pip for managing Python packages, and they provide this requirements.txt in which you can specify the versions of different things that you want to be working with. It goes sort of a step further, though, if you dig into the documentation, and they propose using this process to kind of be really careful in handling the interrelated dependencies of all these libraries and using a build requirements approach where you specify something that looks like this that's called like requirements.in, and then you kind of compile that into the exact version of each of these that you're going to use and maybe other stuff. And then you actually build your environment using that pip, this Python package process. Later on, I'll talk a little bit about how MLflow approaches that. But I would say Kedro just works with these requirements.texts, which are kind of a typical way of handling versioning.
Okay, and it looks like we got one more question from Andrew. He wants to know what type of tests you are running on the airport taxi time results.
Sure. Yeah. So this is a bit of a extension. I don't know, maybe a hack that I've done of the Kedro process. So one thing I do is, very basic sort of reporting model metrics, kind of accuracy type metrics. But then these 3 over here you see are all tests, and these are more like unit tests for a model to check if it's ready for deployment. So here I'm checking like if some features are missing. There's stuff built into the model, and I'll talk a little bit about what that is later, that handles, say, a missing feature and still produces a prediction, does some kind of imputation. Category exclusion. So this is like, for example, the runways. Certain runways I like exclude from usage in my model and have it like return a default for like a rarely used runway, for example, and I have a test for that. Here I'm testing for unknown features. If I have a categorical feature and I'm expecting, 1 of 5 categories, but then in the real operation, a 6th one shows up, I have a way of handling that in the model. So these are more like unit tests down here. And I just throw those at the bottom here. And actually, it's not so much a hack of Kedro now that I think of it. It's really a hack of MLflow, perhaps, where I log those as though they are accuracy-esque metrics, but they're really like binary 1 or 0, like did you pass the test or not? And then I can sort of see that in the MLflow interface that I'll show you in a minute. Okay.
And real quick, Julian just asked, how are test failures communicated back?
Yeah, I'll show you that when I get to the MLflow interface. All right, so I think I'm going to try to keep us going here. In the interest of time, actually, I don't know. Like, should I try to finish up at 8 o'clock, Elliot? I'm guessing that'd be a good goal.
It would be a good goal. Then, if you have more to say, we can hang out on this line and continue. But let's try and get the meat of it done by 8.
Sure. All right, well, let me keep going then. So next I'm going to talk about poor collaborative tracking of model parameters and performance and clumsy model handoff for deployment. So here my example is, again, some chat messages with a colleague, and here we're just kind of going back and forth talking about different notebooks and what performance were we seeing there, the mean absolute error, and here's showing her a little screenshot of the performance I saw, and oh yeah, that is pretty good performance. I think we can do something to get better though. And then later on, she's kind of talking to me about, I ran this other model in this other notebook, and yeah, the performance is kind of comparable, and there's some, we're still getting inconsistent results because we forgot to set our random number generator seed, and so let's try and nail down that parameter for our future runs. So probably kind of common dialogue back and forth between data scientists, but it can become kind of inefficient and hard for me to know exactly what runs has she done, and what run she can't know exactly what runs I've done with what parameters, and meanwhile I'm forgetting what runs I did weeks ago, and so it's easy to lose track, and model performance can suffer as a result. So MLflow has a nice capability of experiment tracking to help improve this sort of thing. And I just put a couple relevant quotes from their documentation. So it's an API and UI for logging parameters, code versions, metrics, and output files when you're running your ML code, and makes it easy to visualize the results. So that's how we'll see the test results pop up there. And then you can also log and query experiments with these various APIs. So the way this shows up in your code, I'll just show you for our iris example here first. After you fit your model, you log your model and log the parameters using these MLflow APIs. And then similarly, after you say report on your accuracy, you, with the MLflow API, can log a metric and even set a tag, like give a model a version. So here I'm logging the accuracy of the model. So that's how it shows up in your code. And then the user interface, you'll see, looks like this. Actually, before I show you this, let me show you how you run the code. So here I have a PowerShell terminal that pops up in the bottom of my IDE. And I've set a few environmental variables that are important to have all this work correctly. But then, once I've set all that up, I can use this MLflow run command to kick off a run. The first thing MLflow does is actually tell Kedro to kick off a run. They both have a run command, but we kind of wrap MLflow around Kedro. So if I kick off a run here, we'll see that it starts telling me things about what it's doing, and it's very fast, but it's running things like, okay, here I'm splitting the data, here I'm standardizing features, training the model, etc. And then if I want to go and take a look at that run, I can go to my MLflow user interface, and there's just a MLflow UI command you can execute to see this interface, kick off this little browser tool here. And here's our run that just happened at 1933. I can see, what were all the parameters to it, what exact commit of the code was I using, how long did it take, when did it happen, and then I can see the metric. So here's the accuracy metric. That's the only metric I'm tracking right now. Also, I can take a look at the pickled model that was resulted from it, and then also a specification of an Anaconda environment that could be generated to run that model. So that gets back to the environment issue that someone brought up before. This is an environment that's potentially different than my model model development environment where I might have like fancy data visualization packages installed so I can explore the data better. When it comes to actually running the model, I may not need all that. And so what MLflow does, and to be honest, I still haven't figured this all out and haven't gotten it to work perfectly for me, but they generate a little environmental specification for you that should be just what you need. So that is the experiment tracking. That's all happening locally just on my laptop. If I go over here to our more kind of production grade system, we have it set up running on a server. And here I can see, runs done at different times by different users. So my most recent run here was done on my laptop with a particular git commit and set of parameters, and you can see the performance metrics. And here, these are those tests that Julian was asking about, and they're just 1 or 0. If it was a 0, I would know the model had failed. And then I see other runs done by other users. This is me logged into another machine. But you can, sort on different metrics. That's not very, meaningful in this case because the model has not been evolving at all recently. But you can do that, and you could even, I think, do like filters. You can even, this looks like you can do almost SQL-esque queries, and it's all backed by a little SQLite database, actually. To just show you a little bit more of what that would look like here, if I kick off a run as that IADS user here on a machine on the same network where that server lives, we'll see it pop up on that experiments UI. Here you'll note I didn't use the no conda thing. The MLflow Anaconda environments, in my experience, don't really work on Windows, but they work fine on a Linux machine like this one. So here it's using a special MLflow Conda environment that it made with that little environment spec I showed you earlier. And it's kind of loading that up and then running the model training and all that stuff in there. This one takes a little longer to run and has many more nodes, but it's reporting stuff to me about it. And once it's done, I can go back here. And if I have to sort this guy, and I should see one that just finished up from the IADS user. So yeah, this is the run that I just did there. So this, makes it much easier to track your experiment runs, and we have these different models here, and I can see the runs done by different people, and you'll see runs done by some of my colleagues popping up in some of these. This could almost, if you are like actively developing with other data scientists and trying to get better performance, this could become like your Kaggle leaderboard almost if you sort on your key accuracy metric and see who's got an experiment that's done best so far. All right, so that's experiment tracking. Then we got another issue that I'll talk about, Clumsy model handoff for deployment. This was something that kind of made me cringe on a recent project at some period in the project. I think we've matured beyond this now. In the repo, I saw these pickled trained models and kind of a lookup table that supported the model hanging out, checked into the repository. And it's great to have a systematic record of trained models, and putting it in a repo, I guess, is better than nothing, but that's not what a code repo is meant for. I mean, these pickled models can be very large, and it's furthermore, potentially hard to identify for a particular trained model, like what version of the code was actually used to make that model that showed up in here, even though it's committed with a specific version. Was it run with the corresponding version, et cetera? So for this, there's something called the MLflow model registry. And I, again, just pulled a few quotes here where you have a centralized store, APIs, UI to collaboratively manage the full life cycle. You have model lineage, so you know what experiment created the trained model. You have model versioning. You can go from staging to production to archive. You can annotate models. All that data about the model and the versioning and so forth is stored in a database. And also model artifacts like the trained model pickle or corresponding supporting data sets. those can all be stored on some other cloud or shared storage. So in our case, that I'll show you, we have like a network attached file system that many people can access, and it has plenty of room, and that's where we dump all of those potentially large model artifacts. So let me flip over to that real quick. So here you can see our registered models. We only have a couple of them here. We have version 3 of this taxi and AMA model in production, and version 2 of this one. And if I want to take a closer look, I can go in here and see, okay, which run. Well, I could move it if I wanted to a different stage. I can see the exact experiment run that created it. So then I know what git commit made it, what were all the parameters, what were all the metrics, what are the model artifacts here. It's on that shared drive that I mentioned. So everyone can go and get it if they need to. So that is the MLflow model registry and the end of what I'll tell you about MLflow, although it does have other capabilities. So I'll pause here. Any questions about the MLflow stuff I just showed you?
We'll give them a second because I think the stream is delayed by a couple of seconds. But right now we don't have any questions.
So, Michael, I'll ask you one question while we're waiting. Do I understand correctly that MLflow is a wrapper around Kedro?
It can be. In this case, it is in the sense that the MLflow run invokes a Kedro run command. These two things can be used entirely independent of one another. They're developed totally independently of each other. Kedro by this Quantum Black data science consultancy that was acquired by McKinsey. And then MLflow came out of, I want to say Databricks, I think. Should know that. I think it's Databricks. But the Kedro folks started, or I heard about early this year or late last year, them kind of promoting the two of them working together. And maybe, while we wait, I can just show you a backup slide I have here. That there's a nice, there's some overlap in features between these two, but they also provide pretty distinct features. Kedro focuses a lot on like code organization, pipelining, forces you to sort of apply a standard process and some rigor around how you set up your project. And then MLflow is more about tracking like your experiments and the models as they go along the way. And they had some kind of analogy, something like Kedro is like what you use to build your factory of models, and then MLflow is more about like tracking the performance of the models kind of coming out of the factory, something like that. So you could use just one or the other. I'll say more maybe later, but Kedro or MLflow is much easier to just kind of pick up and like strap onto any data science project. It's pretty lightweight, just a few little commands and environmental variables, and off you go. Kedro, it's like you probably want to just start from scratch and implement a data science project from the beginning using Kedro. I went through the process of refactoring a non-Kedro project into a Kedro project, and it was very painful and time consuming, and I wouldn't recommend it. I would say like wait until you have a new project and then try Kedro and use it from the very beginning. And they even have some interesting hooks into like Python notebook, Jupyter notebooks, so that like from the very beginning, you're using the data catalog and the parameters, even when you're kind of tinkering with things in a notebook, and it makes it like easier to transition into the scripted pipelines.
Got it. Hey, thanks.
Sure.
Thomas, are there other questions?
We got a couple questions. So Julian wants to know, is there a built-in model tracking, and are we able to track how the model is doing on new data going forward, as well as how does it handle drift?
Oh, okay. Like once the model is deployed, like how is it doing, kind of a thing. I don't think that is built in. I think you could probably. They both say they support deployment, and I know what they mean, but I don't think it is like model monitoring. So yeah, unfortunately, I don't think they directly support that. Although I could imagine how one might sort of hack MLflow, pretend that your production predictions, assuming you get a corresponding ground truth label from them, you could sort of pretend that your actual deployed predictions were a new experiment and log the results on a special project or group of experiments on MLflow, and you could sort of turn it into a bit of a model monitoring tool, but I don't think it's designed for that, and there's probably other tools that would be better suited to that.
Okay, and then we got one other asking, does MLflow support scikit-learn? And if so, how does parameter logging work in distributed computing?
I don't know, but I'm pretty sure that MLflow works really well with PySpark and some other maybe distributed storage and certainly like cloud storage. But I personally haven't used it for that, and I couldn't tell you how it does so.
Yeah, it looks like all the questions we have.
All right. Well, I'll keep going then. I just have one more opportunity for improvement to talk about with you here, and this one I'm just going to use an example from our Iris project. So you remember from the pipeline that I showed you before, part of the data engineering pipeline was this standardized features node here, where you take all the features describing like the width and the length of the petals, and you standardize them so they have a mean 0 and standard deviation 1. And sometimes that's something you want to do for model interpretability or to facilitate the model training. In this case, it actually doesn't help or hurt, but I just did it for illustration purposes. So yeah, say you do that as part of your data engineering work. You figure out like, oh yeah, let's in feature engineering work, you say, okay, yeah, let's do this standard scaling. And then you go off and train your model downstream in your pipeline, like what I showed you. When it comes time to deploy it, you might have this like pickled model object, and you did it all with the MLflow, and so it's really slick and it's right there with the environment, and you try to hand it off. Well, then an issue that can arise is like, all right, who's going to do this standardizing of features once you have it out in the real world? Maybe the software development team says like, okay, here you go. Here are your measurements of the width and length of these new petals on this plant. Tell us what kind of plant it is. And if you just naively throw them into the model, it won't give you a meaningful prediction because you need to do this scaling first. And that involves keeping track of some parameters, the adjustment for the mean and standard deviation. So one nice way to handle that, and a lot of things like that, is using scikit-learn column transformers and pipelines. And at a very high level, they kind of enable you to take stuff that you might do or think of yourself as doing as part of your data engineering or feature engineering and bundle them right in with the model. And when you do like the dot fit, it sort of learns any corresponding parameters like that mean and standard deviation for your standard scaler. It maybe could learn how to impute something or do a one-hot encoding. And there's really tremendous flexibility. You can code all your own versions of these column transformers. And then when you call .predict on like a new instance, an unseen instance, it will not just do the model prediction with your logistic regressor or whatever, but do all the transformations as well. And so everything like stays together, and there's a very high degree of reuse. So these words here probably say about what I just said, but you can create a separate pipeline for each feature you want to feed into the model, so you can multiply together two kind of things that come in raw to the model to create a new feature. You can provide, do these common processing steps, impute things, do one-hot encodings or other encodings. And then you stitch these all together into another pipeline. It's just an overloaded term here. There's the Kedro pipelines we've been talking about, but now we're talking about something that's a little smaller in scope, the scikit-learn pipeline. That's essentially a bit of like data engineering and feature engineering and a model all bundled together that can all be fitted and trained together, and then also all operate together in like a dot predict mode. And then your model becomes a grander object that does this connecting and transforming of raw data and getting it ready for the model, as well as doing the prediction. So here is what some code looks like to do that, and it is unnecessarily verbose, just for illustration purposes. But here I'm making a column transformer that operates on the 4 columns of raw data that we have coming in. So it's a column transformer that is a list of these 4 transforms, each one operating on one of our kind of feature columns. They all do the same thing. They all do a standard scalar, and I give them different names. And then I build a model pipeline that consists of this column transformer that operates, separately on all of these guys. And there's also this remainder pass through, just lets the others kind of go through. And then the model. So it transforms the data, and then it does the modeling. And then you just sort of proceed as before. You fit just like you did before. You log the model just like you did before. It shows up and can be used to make predictions, but the predictions are really doing data engineering feature preparation as well as the actual predictions. And your pipeline ends up being simpler. This is what the revised pipeline looks like. You see there's no longer any standard scalar here in the data engineering portion of the pipeline. In the old version, we had this standardized features. Now we don't have that because that's all happening in the model, and it stays with the model forever, and you can't have any errors when you kind of re-implement. So with that, I will give a few reflections and the main message, and then we can see if there's other questions. So both Kedro and MLflow are relatively new open source software, so the documentation and support is kind of spotty, and we've seen things changing and kind of breaking from version to version. So just kind of an FYI there. I mentioned this before, Kedro is quite opinionated. It really wants you to work within its structure, which is probably good for you. It makes you follow best practices. It makes sure that things are reusable, reproducible. It's easier for people to bounce between projects if they're all going to follow this same structure. And it's a well thought through structure that can also be extended to handle new data sources and things of that sort. So again, the main message for you: ML model development workflows and model life cycles can be complex. Hopefully my little vignettes have illustrated for you some of the pitfalls that are out there. But tools like Kedro, MLflow, scikit-learn pipelines can help you manage that complexity and thereby helping ML models to more efficiently deliver value. And with that, I'll take any final questions that you might have.
We have one kind of miscellaneous question. Andrew's asking what Linux server you're using and what specs.
I don't know. Yeah, sorry.
While we wait, I guess I will ask you a question. How long have you been in this field, and what kind of advice would you have for someone just starting out?
Wow, that's a big question. So how long have I been in the field? I'd say I've been doing data science work for about 12 years or so. I would consider the work I did back when I was at NASA to be data science work, even though data science wasn't really a term back then. I think, like many data scientists of my era, I studied a field that was not called data science proper because that term didn't really exist. I studied mainly electrical engineering and then operations research, but sort of transitioned to data science and found that I really enjoyed it and picked up a lot of the tools and techniques that I hadn't picked up in my academic training, more by just using them, doing projects at work. For someone just starting out now, it's a different world. There's all sorts of data science programs at universities. A lot of those, look really excellent and have a really nice curriculum. There's a lot of fantastic online resources. So I, certainly would encourage you to take advantage of those. Get as much real world experience as you can as well, of course. I would say one piece of advice I like to give is be curious and keep learning. There's just like so much that can can be considered data science. I mean, the talk that I gave you today is maybe more about like software development best practices or DevOps or data management or things like that. More about that than it is about data science in terms of like predictive modeling. And so it's or prescriptive modeling. There's just so many pieces to data science. And that can be kind of overwhelming at times. But I would encourage you to try and stay humble and curious and just try to keep learning. I try to consider curiosity and learning a core capability of mine, and keep understanding new approaches to solving problems. As I hear about them and get interested in them, or as I need them for a project. And some of them are very new developments that just came out in the last few years, and others have been around for many decades and are just tried and true capabilities. I was talking to someone just recently about hierarchical regression. It was not something I ever learned in school, but discovered it in the course of doing a project, and now just find it super useful, and keep seeing new ways that I might want to pick it up and use it.
Okay, thank you for that. And we do have one question here from Andrew. He wants to know what kind of projects have you worked on in the past, and do you have any favorites?
Yeah, man, I've worked on quite a few projects these days by now. Man, I just sort of wrapped up a project where I was doing that I talked to this group about earlier, and you can find my slides and stuff on common filters. And that was a really fun project, and I just was able to write a publication on that. And common filters are super interesting, and for me they connect back to kind of control theory, which was what I studied when I was studying electrical engineering. So it's kind of a cool example of something that maybe originated more in the electrical engineering world, but has made its way into application in the more data science world. And so that was really fun. I also really enjoy reinforcement learning, and I've had a couple chances in my career to deploy that. I've talked about that at another meetup. So I guess I've come and talk to this group about things I'm especially excited about or interested in. And so some of my earlier talks describe the tools behind some of my favorite projects that I've done, at least in the last few years.
I see we're coming close to the end of our time here. Thomas, I see a couple questions that were issued about 10 minutes ago or so. One from Andrew Van Dyke about Linux servers. Did we hit that?
Yeah, I think
it was really short because I didn't know the answer.
Okay. All right. Looks like there are no further questions. And unless there are some here in the last 3 minutes or so, I would like to say a couple words of thanks. Firstly, to Michael Bloem for enlightening all of us on this occasion again about something that is currently useful in the field of machine learning, data science, because it's rapidly evolving. There are new tools coming on the scene all the time, and they're really useful in many cases. And so this is a great example of that. And based on some of the comments that I've seen in the Slack channel that are not questions, I think our entire audience is echoing that sense that this was very useful and helpful information, Michael. So thank you for the time that you put into preparing these really well-delivered presentations. And this is yet another. I'd like to thank Tuyin once again for setting up the technical infrastructure to make this all work relatively seamlessly. And I also want to thank two partners in sponsoring this talk, and they are the West Michigan R Users Group and Machine Learning GR. And so those groups and their organizers have worked with us closely on numerous occasions, and we're always thankful to have them as co-supporters of this type of event. We miss not seeing you all in person. And we look forward to resuming our in-person meetings, but this will have to do in the meantime. I want to quickly introduce you to Thomas, who has been fielding the questions for us today. Thomas is a new organizer of data science in Analytics West Michigan. And Thomas, I'm going to ask you to pronounce your last name because I don't want to make a mistake there.
Right, it's Geib, Thomas Geib.
Thomas Geib. So Thomas Geib is a WMU student studying data science, and we look forward to your participation in this group, Thomas. Thomas, have any other questions come in the meantime?
I believe that's all. A lot of people are thanking you for this and saying it's very useful. So thanks again, Michael. And I think that would complete this live stream.
Thomas?
Yep, I think it will.
There are two questions.
Just,
yeah, I just want to make sure there are two questions and if they were answered. So one of them was from Andrew Van Dyke. Can you give some examples of projects you've worked on? Any favorites?
Oh, yeah. You guys still hear me?
Yes.
Yep.
Yeah. I tried to answer that. I talked a little bit about some reinforcement learning and also Kalman filtering, a couple tools I picked up on some projects. I could go into more details if appropriate.
And there was one more. I wasn't sure if I heard an answer to that one, and I apologize if that's superfluous. And that was from Julian. In the spirit of combining transforms into the model pipeline, do you see data science and data engineering converging, at least in business context?
Yeah, that's an interesting question. I generally have been seeing more distinct roles emerging in the data science domain, like not just data scientist, but there's also, data engineer and ML engineer emerging as kind of a distinct role, maybe more about operationalizing a model. However, the scikit-learn pipelines in particular, and seeing how we've started using those, and one of my colleagues is a big proponent of those, seeing how he's used those has made me think that more of that data engineering work should be incorporated bundled into a more broadly defined model as the pipelines, the scikit-learn pipelines make possible. So yeah, in that sense, I do see them converging. However, I think there's always going to be a distinct data engineering role. There's always disparate data sources that need to be kind of moved around and cleaned up and joined and so forth, even just to be generally available, not just for a specific model. And also, not all feature calculations can or should be done using a scikit-learn pipeline. There are some things that are far too complex and also apply to many instances of that might be sent into a model. And in that case, it would be really wasteful and redundant to recalculate the same complex feature for many example instances that need to be scored or whatever. So yeah, even though many more things can be bundled with a model using a scikit-learn pipeline, not everything can, not everything should.
Thank you. Thank you, Michael. I see one question, and we'll probably take that as the final question. And so maybe, Thomas, you want to take that one from Slack?
Yeah, is it by Tyler Reed?
Yep.
So he's asking, he's a new graduate and student at Grand Valley, and he's overwhelmed with the number of directions that he could go with data science. He wants to know if you have any ideas how he could narrow down on an interesting field.
Yeah, that's a good question. One way you could go is by focusing on a particular domain. Maybe it's medicine or medical imaging, or maybe it's finance, or trading and financial markets. Maybe it's in my case, just the way my career has played out, I've kind of honed in and specialized on air transportation and aircraft and predicting things about when they'll be, where they'll be when, and suggesting ways to adjust how and when they fly and that sort of thing. So that's one way that could be fruitful for you if there's a particular application that you're very interested in. Data science, there's a lot of tools that can be used in many different fields, but any individual field also has a huge body of like subject matter, and there's a lot of subject matter expertise to be learned. And to deploy those tools well, you probably need to spend some time understanding the context in the field. So that would be one way to go. An alternative way to go might be sort of the opposite, and like focusing on a particular tool set, like image processing and or NLP, and just get really good at that tool set, and then be able to apply that in all the different domains that it pops up. That probably is another kind of reasonable way to go. I have a colleague who really specializes in like time series analysis and forecasting. And when we have projects that come up of that flavor, we often pull her in to provide that expertise. So yeah, those are a couple of ideas that come to my mind. Those are helpful.
Thank you, Michael, for answering that final question. And with that, I would like to say goodbye, and thanks to everyone in the audience for your questions and comments. And although this is a little impersonal, still it's a lot of fun. And I want to invite people to offer to present. So almost everyone knows something that is new and relatively unknown to everyone else. And so we invite you to submit a proposal for a talk. I'm sure Michael would be willing to coach you on how to give that talk. We would as well. So we look forward to hearing from others with things that are equally interesting. Everyone be well, and we look forward to seeing you the next time. Take care and good night.